Welcome to Dementia Matters, a podcast presented by the Wisconsin Alzheimer's Disease Research Center. Our podcast is here to educate you on the latest research, caregiver strategies, and available resources for fighting back against Alzheimer's disease. I'm your host, Nathaniel Chin. Thanks for joining us. Today on Dementia Matters, my guests are Rebecca Koscik and Tobey Betthauser, both PhD researchers at the University of Wisconsin-Madison. Dr. Koscik is a senior scientist in the Wisconsin Alzheimer's Institute and Wisconsin Registry for Alzheimer's Prevention, WRAP, study, where she has studied Alzheimer's disease since 2003. Dr. Betthauser is an assistant scientist researcher in the Wisconsin Alzheimer's Disease Research Center, where he studies advancements in brain imaging and cerebrospinal fluid biomarkers of Alzheimer's disease. They are here with me today to discuss their recent research on a new concept in Alzheimer's disease research, and that is amyloid chronicity and amyloid and tau trajectories. Welcome to Dementia Matters.
Thanks
for the invitation.
Now, before we delve into the science, I want to start this interview with a question I ask a lot of guests, and that's what got you interested in this field of Alzheimer's disease and dementia research. Now, Dr. Koscik, why don't we start with you?
Thank you. That's a really interesting question. So I've worked as a statistician since 1989, but after working in statistics, I realized I wanted to do more, and I went back and got my PhD in educational psychology with an emphasis in school psychology. So I learned a lot about cognitive assessment and developmental occurrences at the young age of the developmental spectrum. But then I realized I missed research, and there was an opportunity to come back to the Department of Biostatistics because they needed a statistician who also understood cognitive assessment data. So that was how I came back into research at the medical school, and I started, it was a cystic fibrosis project with adolescents, but then I came on board with Dr. Sanjay Asana's research group, and also began working in Alzheimer's disease. And so that's how I got here.
Started with the young and are ending with the old?
Yes, there's a lot of similarities between the two ends of the spectrum.
And cognitive milestones, which is true throughout our entire lives.
Exactly.
Well, now, statistics are important in research. They're extremely important when studying diseases of aging, where we're looking at changes over decades and not just a simple experiment. So in Alzheimer's disease, how we analyze data is critical. So can you share with us what you've learned from all of your work on Alzheimer's disease and the importance of using good statistics?
Yes, that's a great question. In fact, I'll expand it a little bit. It's not just good statistics, but it's good statistical design. So making sure we have enough people in a study to answer the question we're interested in is important to knowing if the results we got are reliable indicators of what we're interested in. So that's sort of in general about statistics, but in Alzheimer's specifically, one of the really exciting things we get to do here because of the WRAP study and the Alzheimer's Disease Research Center's parallel study is we get to look at what's happening before clinical symptoms appear. And so with good statistics, we can detect really subtle early changes. And we can help figure out sort of the implications for clinical relevance. And then we can also help learn the earliest changes in the biomarkers that are related to the brain pathology associated with Alzheimer's.
Well, on another part of the research, so Dr. Betthauser, how did you get into your particular field within Alzheimer's disease research?
Sure. So I actually started out as an audio engineer, which doesn't seem like it would have many parallels to Alzheimer's, but I'll get there. But this was around 2010. I decided to get out of it. I wanted to do something that was a bit more impactful. I didn't really feel like my contribution was much just making music all day long. So I got into physics and then wanted to go into something more applied, so medical physics, which is more or less the application of physics to medicine. And a lot of that is in the worlds of oncology and also any kind of like medical imaging scan you could think of, so like an X-ray, a CT, PET imaging, positron emission tomography imaging, which is really where my background is. I was fortunate to land in Dr. Brad Christian's lab here at the University of Wisconsin. He does a lot of really impressive developmental work on PET radio tracers that we use to track different brain targets. And the field and the ADRC here were just getting into tau imaging, and so I was able to get a lot of experience there looking at tau, which is one of the protein aggregates that we look at in Alzheimer's disease. So I kind of, it was a little bit of serendipity and a little bit of purposeful drive once I got into it. And then with Alzheimer's too, I have a family history, on both sides of my family. So it's very nice to work on something where you can make a direct impact.
And because we can't actually go into people's brains, we need to have a way of studying the brain in live time or sort of live time that's protective of them, but also helpful to us in figuring out what changes are happening that are normal versus abnormal, and over time, what do those abnormal changes mean?
Right.
And that's something that you in particular look at.
Right, and I think to add to that too, I mean, I like to draw parallels to cancer research because I feel like it's there's a lot of parallels there. The thing with most cancers is that they happen on a truncated time scale, right? So from the time you can detect a cancer to when you reach some clinical endpoint, it could be a matter of 3 to 5 years, right? Alzheimer's disease, we're talking decades. So we're kind of in it for the long haul, as Rebecca suggested. We really need studies that are designed kind of from the initial phases to look at these things. And then we have to figure out what they mean, right? I mean, we can look at these amyloid and tau biomarkers. We can say whether they're elevated or not, but we need to get that context of what does that mean clinically for somebody now or 5 years from now, and then of course there's a bunch of implications for clinical trials and prevention trials and things in that world as well.
Well, then let me ask you, now when talking about research dealing with amyloid PET scans in particular, I often hear people refer to elevated versus non-elevated, or positive versus negative, and some people even have said sub-threshold versus over the threshold, which makes it all very confusing for people not in the field. So can you talk a little bit about the tracer, the amyloid PET tracers themselves, how they work, and what are you actually measuring when we get these scans?
Right. So, I mean, the goal, right, is to track the pathological process. So, in pathology, we can look under a microscope and we can see these changes. So, again, drawing the cancer parallel, if you go in for a tumor biopsy, a pathologist can put that on a microscope. They can say you do or don't have cancer, right? With the brain, it's much more difficult. Obviously, we can't be taking tissue sections of the brain during life. And so we need imaging techniques and non-imaging techniques to be able to look at the in this case proteins, but just the biological markers of a disease process. And so with PET, we're able to have they're no different than any other drug, except for there's much less of it when we inject it. And there's a radioactive isotope attached, and we can detect the radiation that emits from that isotope. So what that allows us to do is to take a drug, inject it into a person, and then we can follow the distribution of that drug throughout the body, and in this case, the brain. And we can do some pretty nice fancy methods to get at determining the amount of say amyloid or tau within some part of the brain, some region of the brain. And as it comes to detection and things, there are many processes that can affect detection, and I think that that's one of the things that we're really starting to learn with this longitudinal analysis that both Rebecca and I have been working on, is where is that meaningful signal? It's similar to what Rebecca was saying about there's noise in the cognitive data. Well, there's noise in any data, and we have to understand what that noise is and what's meaningful signal in that noise and how to pick that out. Yeah.
So two things about that answer I want to clarify. One, isotope, is that more just a chemical?
So that's it's like an element on the periodic table, right? But it's radioactive. So it's the types of elements that you use for PET imaging are not the stable isotopes that you see on the periodic table of elements. So those that will sit there indefinitely, in some form forever, right? But with radioactive isotopes, they undergo radioactive decay, and there are very specific physical processes that determine how fast that happens. But by they emit particles when they decay, and we can actually detect those particles.
So you want them to decay so that you can pick up the signal.
Right, we need them to decay.
And then the second part, because you've said the word a couple of times, and I want our audience, especially our participants, to hear this explanation. Radioactive usually is thought of as a scary term, but in this regard, we're not fearful of the radioactivity.
Right. So there are a number of studies that happen before any kind of PET tracer makes it to any human research. There's toxicology studies that happen basically in a petri dish or in animal models. And all of these things give us some indication of the safety of the tracers we're injecting, right? And so that includes, like what a typical drug would have. So if you're developing a new drug like aspirin, right, or something, right, you need to know at what level is it effective, but also at what level is it dangerous. So all of those studies happen prior to getting into humans, and then on the radioactive element of it, we do what are called dosimetry studies to understand how much that radioactivity is effectively delivering a radioactive dose to the patient, or in this case, participants. So there's a challenge in radiation dosimetry that, very low levels of radiation, it's hard, you can't really do a proper study in humans. So, you can draw parallels to things like flying on a plane from New York to Los Angeles, or other types of radiation exposure that are equivalent to a PET scan that are thought to be safe.
Well, with that too, I want to move into this very important publication. You have two of them. I want to start with the one that happened in brain. I know the other one happened in what exactly?
Alzheimer's and Dementia, the Diagnosis, Assessment, and Disease Monitoring Journal.
Okay. Well, so let's start with the one in brain. And I say important, but really it's quite novel what you guys are showing. And so if we could start by explaining to our audience what exactly you were looking at, and then what you found.
Sure. So I think to begin with, I think it's important to understand kind of the timeline of when things became available. So Rebecca mentioned the RAP study being around since around 2005. So we have all of this cognitive data that's been collected over this period of 10 or more years prior to when some of these PET tracers became available. So one of the PET tracers that has only recently become available is MK6240, and this looks at tau tangles. So we're just kind of now getting a picture of what tau looks like in the brain with this radio tracer. And so that was kind of where we anchored the time point to. So we said, okay, people had this tau scan, and then they had 8 or 10 years of cognitive tests prior to that tau scan. And what we wanted to know is, based on their tau scan and their amyloid scan that happened at the same time, we can determine kind of people that have elevated levels versus not elevated levels of amyloid and tau based on imaging. And then we can look backwards in time and say, how did these people perform, in the previous 8 years before we had these PET scans? And so the big research question we had was, one, did these people perform differently over time? So we had 4 groups: people that could be negative for both amyloid and tau, people that could be positive for just amyloid or just tau, or positive for both amyloid and tau. And we compared how those 4 groups, people in those 4 groups performed over time in that previous 8-year period. So we wanted to see if those, what we're calling cognitive trajectories, so their change over time, if those differed between those biomarker groups, and then if so, how were they different? So that was really the main analysis. And what we found was that, so this was 167 people from the Wisconsin Registry for Alzheimer's Prevention, and this was, the imaging was mostly conducted under Dr. Sterling Johnson's PREDICT study. And what we found is that people that had elevated levels of both amyloid and tau on imaging had been declining much faster compared to any of those other groups, and that those other groups were not different statistically in longitudinal cognitive performance. So it's kind of a first step in this early detection idea. So all of these people were cognitively unimpaired when they started the study, so we could say normal cognitively. So we found that only 6 of these people were MCI, had mild cognitive impairment at their PET scan, and all of those pretty much just became MCI at their last cognitive visit. So what we were seeing is that these cognitive changes were occurring several years before the PET scans, where these people that had both higher levels of amyloid and tau at the end of the study had been declining for several years before we did those imaging scans. So it's kind of a first step towards understanding what these biomarkers tell us about how somebody is going to perform related to Alzheimer's disease. So it suggests that people with both amyloid and tau are declining faster in cognition, even during this phase of disease where they haven't met clinical levels for cognitive impairment.
And then how does this study relate to the most recent publication that you guys have had in Alzheimer's and dementia?
So the most recent study we published is a paper where we're looking at translating this measurement of how much amyloid is in the brain at any given time to an estimate of how long has amyloid been present in the brain. Because we have a lot of people, somewhat like a little over 70%, who don't have evidence of amyloid in their brain yet. And then we have people with varying levels. So this earlier conversation about PIB positivity or amyloid positivity versus subthreshold or things like that, there's a ton of interesting questions that can be asked about, is it being over a level that matters, or is it how long it's been present in your brain that matters? Because there is a theory, a cascade theory in Alzheimer's disease that the pathology begins with amyloid, or that's at least one of the earliest things, and then because of that, other things may begin to happen. So this most recent paper, it's work that Tobey and I and Dr. Johnson and others have been working on and thinking about, can we translate this measurement of amyloid into a duration of burden? Because we think that understanding it might improve our clinical trial design by selecting people that are in a critical window, or some treatments may be more effective at this stage of amyloid duration versus others. It will help us understand which pathologies develop first and second. So with the tau and the amyloid imaging work that Tobey's doing now, we're beginning to see that there's a gap in time where we're seeing more evidence that for a lot of people there's a gap between when amyloid occurs and then when tau occurs. So it just opens up the opportunity to look at the questions from a slightly different perspective.
And do we have any findings or any significance to whether or not chronicity, having amyloid for longer, has any impact?
Yes, so in that paper, what we ended up showing was that the longer you have amyloid in your brain, our estimate is longer. And then I just have to put in, it is highly related to how much amyloid is measured, but it's a different way of looking at it. So having had it longer makes a person more likely statistically to be exhibiting declines similar to what Tobey described, either to a point of mild clinical impairment or cognitive impairment rather, or just subtle declines relative to others in our study that say, hey, this is a statistical difference that we think is showing real change. And then we also saw a relationship between this amyloid chronicity or duration and some of the measures of tau. And so that's where we started seeing some of that gap of maybe 8 to 10 years after PIB chronicity. It depends on how you measure it, but we know we can see that there's a lag between when the amyloid is detectable and when the tau is detectable.
You wouldn't really be able to ask these questions or answer them if you didn't have people coming in year after year,
exactly.
Almost 2 decades.
Yes.
Well, and I think you hit on, that's really the key point, like the especially the chronicity work, but even the brain paper, these things aren't possible unless we follow things over long courses of time. We're really learning that this amyloid accumulation period is several decades, 2 to 3 decades, maybe more than that. And that's just what we can detect with PET imaging. We also know that there's stuff that's happening that we can't yet detect with like PET, for example. So, but it's one of those things where, yeah, you can't just look at a single snapshot in time, across a bunch of people and put it together. You really need to know how people change through the course of a disease, and that's really what the RAP study and the PREDICT sub-study are really designed to do.
This chronicity makes a lot of sense to me from a medical perspective, because we know that when you say, for instance, a person has diabetes, well, having that diagnosis matters, but knowing how long they've had that diagnosis, how long they've had issues with sugar, how severe those issues have been in the past, it all varies over time, but it all matters. Mm-hmm. So it makes sense to me, at least, as a non-amyloid specialist, that this would be an important piece of information. The other thing I would like to end with is that question of how some people can have high amounts of amyloid and not develop tau, I think is important, because as a clinician, this potentially is my place of intervention. That are there certain things that people are doing that are building resilience to that amyloid protein, preventing tau? Now that's all speculation, but I think it's important that we have that question, because that is something that people can do without a medication. They can do on their own. Mm-hmm. So with that, I would like to end by asking each of you, what is one thing that you prioritize about your life that you think could be building that brain buffer or reducing insults to the brain that you are just doing intentionally?
Sure. So probably two things to add there. I would say 80 researchers tend to not do a great job of following their own advice. And that's probably an overgeneralization. But, I think the research is pointing to two kind of things, that there's a biological pathway. And at least in amyloid, that timeline and that pathway really seem to be pretty robust to a lot of external influences. So I think that's where Rebecca and I were really surprised to see some of these findings. And no matter what kind of things we throw at it, your health style, things that you eat, how much you sleep, all these things, it doesn't seem to move that amyloid bit much. But that doesn't mean it doesn't affect cognition, right? They're intertwined, but they're not, mutually exclusive. Or what was I saying? They're intertwined, but they're not connected in a way that they don't impact each other and other things can't impact them, right? So I think to that point, there are plenty of things you can do to improve your cognition, right? Sleep, which with young kids and in research I don't get much of, so exercise, diet, you try to supplement some of these other things that at least clear up your mind so you can think better. Those things maybe do or don't affect the biology, but those are questions we're still investigating and we need answers for, especially with these differences in for two different people that have the same level of elevated amyloid, and one of them has tau and one of them doesn't. That's like, why is that different? And we don't know that answer yet. Yeah.
So that's a good way of avoiding answering my question. So, Rebecca, how about you?
I would say I like to prioritize getting exercise and doing exercises I find fun. So I walk a lot, but I walk with friends usually, and that provides some social engagement too. Or I play ultimate frisbee with my daughter and a group of people, and so I find that the exercise is really good for thinking more clearly.
All right, and fun is the right word, because both of you smile a lot and you enjoy your work and you're passionate, so perhaps there's something about purpose as well. Yeah. So with that, I'd like to end, but I do want you both to come back as these results come in and we have more to say about amyloid chronicity and amyloid and tau and how a person is doing over time.
That would be really fun. Thank you so much for the opportunity to be here.
Yeah, thank you.
Dementia Matters is brought to you by the Wisconsin Alzheimer's Disease Research Center. The Wisconsin Alzheimer's Disease Research Center combines academic, clinical, and research expertise from the University of Wisconsin School of Medicine and Public Health and the Geriatric Research Education and Clinical Center of the William S. Middleton Memorial Veterans Hospital in Madison, Wisconsin. It receives funding from private, university, state, and national sources, including a grant from the National Institutes of Health for Alzheimer's Disease Centers. This episode was produced by Rebecca Wazaleski and edited by Bashir Adin. Our musical jingle is Cases to Rest by Blue Dot Sessions. Check out our website at adrc.wisc.edu. You can also follow us on Twitter and Facebook. If you have any questions or comments, email us at dementiamatters@medicine.wisc.edu. Thanks for listening.